So now the last session. So this is about the Kronig-Penney square well potential. Kronig-Penney square well potential. So we are going to solve now Schrodinger equation using Bloch function. The Bloch function was suggested by Felix Bloch. He didn't solve. Whereas Kronig and Penney, both they solved. He was from German, Penney from UK, Lord Penney. In fact, Lord Penney did his PhD in mathematics. He studied mathematics in UK, but he got his PhD earlier to mathematics. That is, in the year 1935 he got his PhD in physics. 1936 only he got his PhD in mathematics. So he got two doctorates. One is in mathematics, another one is in physics. He worked along with Kronig and they solved Schrodinger equation for this, but they did not get Nobel Prize. Okay, Kronig and Penney. They got many medals, awards. Okay, so this we discussed already, correct? We discussed already. This is about the potential energy diagram when positive ion is here. So we have written the positive side. So last time we discussed in the negative side. So positive ions are here, nucleus is here, and this is the potential energy diagram, correct? So at this point, that is at 0 point, origin point, it will be the maximum value. So it will go to the infinity. According to the equation, V equals minus E squared by 4 pi epsilon naught R. So we know already this one. And also very important thing is the bands will be formed. This is about 1s square, 2s square, 2p goes on. So bands, energy bands in which electrons will live. Okay, they will have to obey Pauli's exclusion principle, of course. So these are the diagram. Now electrons will move in a periodic potential. So we are going to solve using Schrodinger equation. We are going to solve for psi. So this is the idea. We are going to get the energy. Let us see how it works. We will have to use Bloch's wave function. Okay, Bloch wave function is u of x equal to e power ikx u of x. Psi of x equal to e power ikx u of x. So this is your Bloch wave function. So pre-quantum theory, it was suggested by Sommerfeld. Okay, that the electrons move in a constant potential. So this was suggested in a metal, suggested by Sommerfeld. But it could explain, however, it could explain the L2 conductivity, specific capacity, thermionic emission, thermal conductivity, and so on. But it fails to explain this part. Is very, very important. Why? There are some in solids. We have some semiconductors, metals. We have insulators. So three types are there, correct? And why some solids are semiconductors, some are insulators, some are metals? It could not explain. So that's the reason. That's why Kronig Penney, they suggested one model, and they could explain clearly why some solids are semiconductors. It depends on the band gaps, and some solids are insulators. So according to Kronig Penney model, the electron moves in the periodic potential, which we are going to see now. So this is the Kronig Penney model. So rectangular potential barrier. Okay, so we have a rectangular potential barrier. We have, this is your potential well, this is your barrier. Width of the potential is A, width of the potential barrier is B. They are not equal. Okay, A is not equal to B. And height of the potential is nothing but V0. The potential inside the well is 0. We are going to consider. Okay, and these are all your lattice points, lattice ions. Okay, electrons move in a periodic potential. So this is a approximated one, but the reality is this one. Okay, this is the reality. We have approximated into rectangular, square well and barrier potentials. We have approximated. So in this model, it is assumed the potential energy of an electron has the form of periodic array of square wells. Okay, rectangular wells, so square wells. Region 1. In the region 1, so this is your region 1. X lies between 0 and A, where the potential energy is 0, and the electron is assumed to be free particle. So potential energy is 0. So electron will be always free here. So it's a free particle. So this will have only kinetic energy, no potential energy. Suppose in this region, between minus B, X lies between minus B and 0. the potential energy is V0, the height is V0. Okay, here it is V0. 0 minus B and 0, it is V0. It is A and B. Here it is A, between A and B. Here it is between minus B and 0. Hence the period of the potential along the x-axis A plus B. If you add these two, so that will be your period of the potential. Now, according to Bloch's theorem, so they have used Bloch's idea, V of x plus n A plus B, which is equal to V of x. So this is the potential barrier. V of x equal to 0 in this region and V of x equal to V0 in this region. Okay, so this is the well and this is the barrier. And of course we know Schrodinger equation is given by, in the first region, given by this equation. Okay, we know kinetic energy plus potential energy is 0. Okay, potential energy 0 inside the well. So we have total energy. Okay, so here potential is not because this barrier height is there. So in the region 2, it has like this. And your K1 is inside the well, K2 the wave vector is inside the barrier. So they are given by these expressions. Okay, so instead of 2mv by h bar squared, you can replace with K1 squared. That will give you K1 squared psi 1 of x. And this expression can be written as like this, with K2 squared psi 2 of x equal to j. These two regions. Okay. As I said, we will have to use Bloch functions. Okay, Bloch function. Wave function is known now. So in the earlier case, all the three models, we calculated the wave function. Okay, now wave function is known. So wave function psi of x equal to u of k. K is the periodicity. So u of k of x e power I kx. Okay, so this k, that k is the wave vector. Where u of k of x is the periodic function of x with the period a plus b. Now you substitute. Okay, substitute in the first region. We are going to substitute psi 1 of x is replaced with u of k of x e power I k of x. So we are going to replace. So I have written the same equation 2.124, 2.124. Now we are going to differentiate. Okay, so keeping d by dx as like this. So we have d squared by dx squared. So I have taken one differentiation out, d by dx, and I am going to differentiate with respect to x this term. Is it clear what I am saying? So we have to differentiate two times. So I am going to take one d by dx out. I am going to differentiate only once. So differentiating once, that will give you, keeping this as constant, you will have to differentiate. Then keeping this as constant, you will have to differentiate. So this is UV method. So now we are going to differentiate first. So du1 by dx, keeping this as constant. Now keeping this as constant u1 of x, you will have to differentiate e power ikx. That will give you ik e power ikx. Is it clear? That this term is, let it be like this. Is it okay? 2.125. Okay. Now we will have to differentiate again. So here we have two terms. Here also we will have two terms. Totally there will be four terms. So keeping this as constant, you will have to differentiate, plus keeping this as constant, you will have to differentiate. Similarly on the other side, in the second term. So now we differentiate this. So that will give you d squared u1 of x divided by dx squared, keeping this as constant, plus ik is here. You are going to differentiate. So that you are going to differentiate. Sorry, keep this one du1 of x divided by dx e power ikx. Now ik, let it be as constant. You are going to differentiate. So that will give you du1 of x by dx, keeping this as constant. Ik, you are going to differentiate this. That will give you ik u1 as it is e power ikx. The last term, let it be like this. Now these two terms are same. Just add these two. So that will give you 2ik du1 of x divided by dx e power ikx. All the other terms are, let it be like this. Is it okay? And of course you have multiplied ik multiplied by ik, this will give you minus k square. So this term is like this. We have added these two terms and we have written like this. And this term we have simplified. The last term, let it be like this. Okay, equation 2.127. Divide throughout by e power ikx. So we can eliminate e power ikx. So we have eliminated. Okay, put together we can write this as k1 square minus k square. K1 is a wave vector inside the well. Correct? K1 inside the well. The same expression can be obtained with K2 in the second region. We just replace with k1 squared with k2 squared. That's all. So k2 is a wave vector inside the barrier. K1 is inside the well. What of this k? K is a wave vector 2 pi by lambda. Okay, so don't forget. Okay. Now, where that is okay, where un of x represents the value of uk of x in the interval x lies between 0 and a, and u2 of x, this is u2 of x, represents the value uk of x in the interval in the barrier. So this is for well and this is for the barrier. Un of x for the well, u2 of x for the barrier. So solutions of the above equations given by. So you have to now go for with the solutions. u1 equal to is given by this and u2 is given by this expression. So this is a solution in the well region. This is a solution in the barrier region, potential barrier region. So now A, B, C, D are constants. Okay. Now we have to use the boundary conditions. We are going to use the boundary conditions. So the relations between the coefficients can be obtained from Bloch's theorem. The wave functions and the derivatives must be continuous, as we have seen earlier, at x equal to 0, and they can be determined by the following boundary conditions. Okay, at the boundary, un of x equal to, which is equal to u2 of x at x equal to 0, and derivative also will be equal at one of the boundaries at x equal to 0. Okay. So using this boundary conditions into the wave functions, we can obtain a plus b equals c plus d, and derivative that will give you this expression. We have already known, we have already seen many times. Okay, so use this boundary condition at x equal to 0 will give you a plus b. You just calculate, you can say clearly. For example, x equal to 0 you will have a, x equal to 0 you will have 1 e power 0, so that will be 1. So again b, so a plus b. Here it must be equal to, they are equal, so it must be equal to 0. So a plus b equals c plus d. Okay. Similarly, using another boundary conditions, derivative also at the boundary that will give you this expression 2.134, and you can use another boundary condition at the next region at x equal to a and x equal to minus b. Okay. So similarly, and derivative also. So using this you will get two expressions, equation 2.136 and 2.137. Okay, at x equal to a. Earlier we said x equal to 0, correct? Next one x equal to a and x equal to minus b. Okay, the wave function matches exactly at x equal to a and x equal to minus b. You will get. So these equations can be solved for non-zero values of a, b, c, d using the determinant. So we can make this equation into determinant. So this is equal to 0. Okay. And this is the lengthier one. This is out of syllabus for you. So you have to derive. So straight away you can write the solution as p sin k1a by k1a plus cos k1a, which is equal to cos ka, where p equals mv0 ab divided by h bar square. So this is the lengthier derivation. We are going to skip the derivation, full derivation, and we have written only the solution. This solution is very important. This solution only will determine whether the solid we can make it into semiconductor or a metal or a insulator. So this is what the idea behind Kronig-Penney model. Quantum theory of solids of course explains everything except this idea. So some solids are semiconductors, some solids are metals, some solids are insulators. How it arises from the solids? We are going to get the ideas using this equation. Look at this equation. So right hand side and left hand side, so they are equal, correct? And this is what we call this as a transcendental equation. So this is nothing but a transcendental equation. You will have to substitute certain values for k, substitute certain values of k1 and p for a. You will have to equate these two. That value will give you energy. So that's the idea. So it's a transcendental equation. It will give the complete information about the possible energy levels. So where permitted energy levels exist, it gives. P is known as the scattering power of potential barrier. How much it can attract with the electrons can be attracted in the crystal. So that says about the scattering power of potential barrier. Where P is the measure of the strength with which electrons in a crystal are attracted to the positive ions in the crystal lattice. How much it can be attracted towards the positive ions. So P is very important. So P equals mv naught AB by h bar square. So P depends on the potential barrier and size of the well as well size of the barrier A and B. Okay. Now we will analyze the cases. When P tends to 0, we will analyze the case, and P tends to infinity, increasing case, we will analyze. So let us analyze for when P equal to 0. When P equals 0, this expression will go off. We will have cos K1A equals cos Ka. It implies that K1A equals Ka, K1 equals K. You just square it. When you square, that will give you K1 square equals K squared. K1 is nothing but 2mE by h bar square. As I said, K is 2 pi by lambda. So 2 pi by lambda whole square. Simplifying. So that will give you just simplify, that will give you h bar square equal to h divided by 2 pi. So your h bar square will be h square divided by 4 pi square. So you will get this, which is equal to 4 pi E squared by lambda square. So get the value expression for E, which is equal to h square divided by 2m lambda square. So lambda equal to h by p. So E equals p squared by 2m. What is this expression E equal to p squared by 2m? Kinetic energy of a free particle. There is no constraint, there is no potential energy. So when P tends to 0, it implies that the particle is free. You just have this in your mind, we are going to explain. Okay. So certain energies, they are not constrained, they are free in the crystals in the band, which we are going to discuss now. So E equals p squared by 2m, which is the expression for the kinetic energy of a free particle. So there exists, in a band, there exists the electrons having this expression p squared by 2m, they are free. So hence the energy of the electron is only kinetic energy. The electrons are free electrons. It represents the nature of the conductor. So in the conductor, these energies are free. There is no constraint in a conductor. So conductor, there is no potential energy. Correct? The electrons are free. So it explains clearly this expression, which you have obtained from Kronig-Penney model. It explains one property. This is about conductor. So E equal to p squared by 2m. Now we will go for P tends to infinity. So P goes on increase, P tends to infinity. So this is expression that we have obtained. Correct? You divide throughout by P. Divide throughout by P. So you will have cos K1A by P, which is equal to cos Ka by P. So P tends to infinity. P is very large value. P tends to. So this expression will go off. Correct? And you will have only this expression alone. So you will get sin K1A, which is equal to 0. It implies that for which values? Sin K1A equal to sin n pi. I can write 0 sin n pi. So K1A equals n pi. So K1 equal to n pi by A. Squaring that will give you K1 squared equal to n squared pi squared by A squared. And K1 is nothing but so 2me by h bar squared under root. So we have simplifying, you will get E equals n squared pi squared h bar squared divided by 2ma squared. This is the expression for energy in an infinite quantum well. So energy in an infinite quantum well. Correct? So when P tends to 0, it shows that only particular energy level it can exist. So earlier we discussed all the particles, they will move continuously in the earlier one with free particle. They are free particle and it can move freely without any constraint, without any potential energy, it can move. So now there is a constraint. It can exist only in a certain level. Only certain level. Okay, we are going to see now. These two things we are going to see. So expression for the energy levels of a particle in 1D box. Okay, we will have discrete energy level. This represents only nature of insulators or semiconductors. Only certain levels only it can exist. Okay, we will see. We are going to draw the graph between the left hand side and K1A. If you draw the graph between left hand side and the K1A, you will get the graph like this. So this is for the positive one and this is for the negative one. You will have exactly symmetry. The same thing will occur in the negative one. Now look at the graph. We have in the y-axis we have P sin K1A by K1A plus cos K1A. In the x-axis we have K1B. And right hand side you have cos Ka. What is the maximum value of cos Ka and minimum value of cos Ka? That will be plus and minus 1. Plus 1 and minus 1. So this cos Ka will have plus 1 and minus 1. So we are going to draw a graph between these two, and we are going to get the solution graphically. It says that this condition, that is this expression, is valid, and only then we can get the solution. For example, where it intersects, and this curve is this curve, left hand side curve is this one. Okay, this is exactly like an interference curve. It is something like sin x by x when 10, which is equal to 1. Okay, when x tends to 0, it will become 1, peak value. It is something like that, interference pattern, correct? So now this curve is the y-axis, correct? In this curve, your x-axis will be, this side will be, you have cos Ka. Cos Ka with the plus 1 and minus 1. So we have drawn the line here, plus 1 and minus 1. This curve and this curve, where it intersects, that will be the answer, that will be the solution. I repeat, this curve is here, and you have this curve where it touches, where it intersects, that will be the first solution. So where Ka equal to 0. Now just look at this curve, here it goes here, it touches here, and this is your another solution. Okay, and beyond this there will be no solutions at all. Only the solutions will exist only within this region, plus 1 and minus 1. The particular solution will be obtained only where it intersects, x-axis and y-axis, where it intersects, where left hand side and right hand side. Okay, now look at this one, Ka equals to 0, so it will intersect somewhere here, and the next one will be Ka equal to pi. So this is your pi region. Now this is first point and this is second point, correct? You just draw this one and this one. You can draw this one. This is nothing but a band. This is allowed band in which electrons can live, electrons can exist. Allowed bands. So these are not allowed bands. These are not allowed bands. This is allowed region. This is allowed region. These are all forbidden regions. Not allowed. Beyond this also not allowed, according to this equation. So now the first solution is A, this solution is this side Ka equal to 0, and the next solution is Ka equal to pi. So within this AB is a small band in which electrons can live. Now we go for the next one. Next region will be, this is forbidden, correct? This side is forbidden. This side is forbidden. Beyond minus 1, so it is forbidden here. And this region will be the same thing, your pi. And this region will be your 2 pi. So pi and 2 pi it exists. The next region will be here. Here it is not allowed, forbidden region. So this side will be 2 pi. So 2 pi and 3 pi it exists. 3 pi and 4 pi. Is it clear what I am saying? So it can exist only certain bands. Certain bands are determined by this equation, where it intersects. Two intersect points you are going to connect. So electrons can exist only within this band. Only. The bands are increasing. So this only determines, you just put it upside down like this, and you have a small band will be here, 1s squared, 2a squared, 2p squared, it goes on. And in between you have a band gap. So you have a band gap. So only electrons can exist only certain levels. So clearly it says that it's an insulator or a semiconductor. Depends on the strength of the band gap. If band gap is around say 1 electron volt or 1.1 or 2 electron volt, it will be a semiconductor. Electrons, suppose if you are going to give some small energy, the electrons will go from valence band to the conduction band easily. Correct? Suppose if insulators band in which we have a large band gaps, say 4 electron volt, 5 electron volt, large band gap, for example diamond, rubber, wood. So we should have large band gaps. Even though if you give more than 5 electrons cannot be trapped. Electrons cannot escape from valence band to the conduction. It cannot go. It has to go beyond that voltage, which is not possible. So that's called the insulators. So in which we have larger band gaps. But here semiconductors will have smaller band gap. Easily it can be tracked. So in such a way that this figure can clearly explain the solids into metals, semiconductors and insulators. Another idea is, supposing P tends to infinity, you just look at this way, P tends to infinity, P is very high, and this curve will be like this, correct? It will be a straight line, because P goes to infinity, it will be a straight line, and there will be no band will be very narrow, correct? Here P is here somewhere, so band can be formed exactly with this thickness. If P is very large, this curve will be straight line and there will be no band. You will have only lines. These lines are individual atoms. So it can clearly explain individual atoms also, the energy of the individual atom. Okay. So this is the way the Kronig-Penney model, the equations in Kronig model clearly explains the solids. So this is the transcendental equation. This is the transcendental equation which we have seen now. It can be solved only graphically. The right side of the equation is an even periodic function, cos Ka. It's an even periodic function, and its value will not change whether Ka is positive or not. It can have values only +1 and -1, where the left side can have values outside this. Okay, so we know already this. Therefore, it can be satisfied only the values of E for which left hand side remains between +1 and -1. Beyond that is forbidden, not allowed. Only certain bands are allowed for the electron, and there are regions of energy forbidden in the crystals. It illustrates how a periodic function, say for one-dimensional lattice, can give rise to a band gap. So it raises the band gap. So these are all band gaps. Okay. This forms the preliminary basis for classifying solids into conductors, semiconductors and insulators. So this is known as band theory of solids. So conclusion is, thus the energy spectrum of the electron consists of large number of allowed and forbidden energy bands. So put together, so we have forbidden energy also there, allowed energy also there. It implies that the periodicity of the potential use of this condition nothing but Bloch theorem. So V of U of x plus n plus a equal to U of x leads to the concept of energy bands in one-dimensional lattice. So that's the conclusion. Okay. So thank you students. We will start today. Okay. Thank you very much.